We are in lesson 56 in Algebra 1 today, and we're going to talk about finite and infinite sets, memberships in a set, and rearranging before we graph, or putting things into the proper format of the line before we graph. So let's talk about finite and infinite. If something is finite, that means that it has a definite, it has a definition. It has a set definition. It is spelled out for us, right? When your mom says your curfew is 10 p.m., you have a definite time that you are supposed to be home. It's not open-ended. But when you become an adult, it's up to you. It's infinite. You can stay out all night if you want to. When you're a grown-up, it's not very smart, especially if you have a job or something to do the next day. But in those terms, we can think about finite and infinite. So typically, when we talk about finite and infinite in math, we're talking about sets of objects or numbers. Real, irrational, doesn't matter. A finite set might look something like this. My curly brackets don't look that great, but this tells us that the members of this set are the numerals 6, 7, 8, 9, and 10. And that's it. That's all that's listed. There are no more, there are no less. It's these 5 numbers, right? This is a finite set. It is defined for us. We're told what's in here. Now, an infinite set might look something like this. This is, if you remember, the set of whole numbers. The whole numbers begin with 0. They have no end. They go on and on and on because you can always add one more. You can always add one more to the last number you can think of. You can always make it grow at least by 1. And as long as you can increase it by 1, it doesn't have an end. So we denote an infinite set by putting what we call an ellipsis. That's these 3 dots here. That's an ellipsis, or an ellipses, some people call it. That tells us the set goes on and on and on and on. All right. That's really all we have to say about finite. This is finite. And that's how it's spelled, F-I-N-I-T-E. And infinite, which is just finite with I-N in front of it. So finite set looks like this, and an infinite set looks like this. And an infinite has this ellipsis, or ellipses right there. That's how you know that it is infinite. All right, so you're going to want to put that in your notes because it will probably be a definition or a question on a test at some point in the future. And you're going to want to be able to flip through and go, okay, yeah, I got that. Right? But just remind yourself of it. So let's talk about some members of a set. When we talk about the members of a set, we don't typically, or not typically, but we don't list members more than once. I might have a set of numbers here. I might have 1, 2, 3, 5, 8, 2, 1, and 1. These are all the members of my set. Okay? But we need to designate these numbers. We're going to call this, I think I'm going to call this set B. The way we would write about set B, we would say that B is equal to 1, 2, 3, 5, and 8. We don't care that 1 is in there 3 times and that 2 is in there twice. It's a member. We don't use an exponent. We don't say it's in there how many times it's in there. We just list that it is in there. okay? We don't care about the rest. We just want to know which unique members are in that set and what the name of that set is. And that's how we would write that. So 4, we have a problem here. We have a practice problem. We have 56.1. And we are going to, here's a set of numbers. We have 1, 0, 2, 1, 0, 5, 7, 4, 5, 7. This is set K. So we need to designate this set. So we're going to call this K is equal to, with our little bracket here. We usually start with the smallest number and work our way up to the highest number. That's the correct way to write a set. So 0 is our smallest, then we have 1, then we have 2, we don't have a 3, we have a 4, we have a 5, we don't have a 6, but we do have a 7. And that's how we would write that set. Easy peasy. Let's do 56.2. We have these numbers in set L. Set L has 7, 15, 0, 1, 15, 0, 8, negative 13, and 42. So we are going to write these numbers down. We're going to say L is equal to. Now, technically, if you want to be correct, it doesn't matter. It doesn't matter what order you put the numbers listed. You can put them in lowest to highest. You can put them in highest to lowest. You could just write them down the way they are. But I find that it is easier to make sure that I have gotten all the numbers if I write it down in numerical order, because then I know what number I'm looking for next and I can tell whether or not it's in there pretty quickly, as opposed to going back and forth and making sure I have everything. And that is why most people write it that way, is because it's easier to make sure you have all the numbers there. So I see my first number, my lowest number, is a negative 13. I don't see any other negatives. I see a 0. I see a 1. I don't see a 2, 3, 4, 5, or 6. I see a 7. The next number I see is 8. Then I see 9. I don't see 9, 10, 11, 12, 13, 14. I see 15, and I see a 42. All right? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That is how I do it, because when I do it in numerical order, I can easily see if I've missed something because I'm looking for the next number, for the next number, for the next number. You know, I was looking for the numbers between 1 and 7, and I didn't see them because they weren't here. But it kept me from getting mixed up and confused by looking for, whatever numbers happen to be there instead of looking for something specific and seeing it's not there. So that's just a thought whenever you're ready to write down sets of how to do it, because the order truly doesn't matter as long as it's complete. So let's look at 56.3. All right, we have been given the sets A, B, and C. All right, so A is equal to 0, 1, 3. Let me draw a line here. I'm going to scooch this up a little bit. There we go. 1, 3, and 5. And B is equal to 0, 4, 6, and 7. And C is equal to 1, 2, 3, 5, and 7. Are the following statements true or false? Well, first let me tell you, we have a little symbol that we use. And this little symbol looks like a curvy E or a pitchfork on its side. This little symbol means is a member of. And there's another little symbol that looks like this with a line through it, and that means is not a member of. You're going to want to put that in your notes. Okay? So here come our questions. Our question is A, 5 is a member of A. B, we have 4 is a member of C, and C says that 5 is not a member of B. Are these true or false? True or false? True or false? So let's look. 5 is a member of A. 5, look, 5 is in A. So this is true. All right, what about B? 4 is a member of C. Is 4 a member of C? No, it's not. So this one is false. What about this one? 5 is not a member of B. Do you see a 5 in B? Nope, I don't. So that means that statement is true. Y'all, this is one of the easiest lessons we will ever do. So if you get it wrong, it's because you didn't watch the video. All right. That's all we have for sets for right now. We'll do more on them later, but this part of the lesson is just introducing the concept and introducing these symbols so that you can know what these symbols mean when you see them again, because you will see them again. All right, I'm going to clear this page and we're going to move on. All right, let me scroll back down. Okay, let's look at some rearranging before we graph. Speaking of graphing, I'm going to pull my graph paper up. All right, I'm going to make this a little bit bigger. There we go, that's better. So often we encounter linear equations that have not been solved for y. And graphing these equations is easier if we first rearrange them by solving for y. So in this problem, this is 56.5, we have been given 3x plus 2y equals 4. All right, so we know that it has to be y is equal to mx plus b, right? This is a linear equation. That's what it looks like. This is not in that format. So we have got to move it around until it's in the right format, and then we have to solve for y. So let's do that first. We're going to subtract 3x from both sides, right? This will cancel. We'll bring 2y down, and it's going to equal negative 3x plus 4. Because the x goes first, over just like over here, right? We want to have our x term, then our b term. All right, now we have 2y. We don't want 2y. We want to have y by itself. So we need to divide everything by 2. All the numbers, all the numbers. So now this cancels. We have y is equal to negative 3 over 2 x plus 4 divided by 2 is 2. Now we can create our table and we can solve. So we'll create x, and then here's our function or our equation to solve. Negative 3 over 2x plus 2, and this would be our y, right? So we'll do this right here. and we'll pick some points right here. I'm going to erase this just a little bit. It's a little bit long. There we go. All right, so now, first of all, let's pick 0 because we know we can pick the b, and that's going to be because 0 times this just leaves a positive 2 behind. Okay, so 0, negative 3 over 2 times 0 plus 2. All right, now, I've always said pick a multiple of the denominator in the slope because that's what you're going to have to divide by, and it makes it much easier if it's divisible by a multiple of this. So let's pick 2, and then we'll pick 4. So if I say negative 3 over 2 times 2, which would be 2 over 1, plus 2, that becomes negative 3 times 2 is negative 6 divided by 2. That's going to be a negative 3 because these two will cancel. Negative 3 plus 2 is going to be a negative 1. All right, if I say negative 3 over 2 times 4 plus 2, that's going to be negative 12 divided by 2. That's a negative 6. Negative 6 plus 2 is going to be a negative 4. Right? Right. Okay. So now we have our points. And now we can graph them. So we make our little graph down here. Make our little graph over here. There we go. And we graph our points. We have 0 and 2. That's our y-intercept. Okay, 0, 2. Then we have 2 and negative 1. 1, 2, negative 1. Right? So negative 2. Oh, I'm sorry. 2, negative 1. 2, negative 1. Right? And then we have 4, negative 4. So 1, 2, 3, 4. 1, 2, 3, 4. And that is 4, negative 4. And you can look and double check to make sure the slope checks out. It's down 3 over 2. So from here, 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. So that checks out. So this compares well to our slope. It goes right along with it. So now we can draw our line in the 3 points that we plotted. There we go. All done with this. I'm just going to straighten up my line a little bit so it looks pretty. There we go. And we draw little arrows. And there is our line. Good deal. That's the way you would do that. So let's do 56.6. We'll come over just a little bit. Actually, I think we'll just use the same little graph. It'll be so much easier. And I'll just change color. All right, let's do 56.6 here. And we are given y minus x equals 0. Well, this is not in the right format. We need y, and we're going to add x to both sides. So this is going to cancel. This is going to equal x plus 0. Well, that tells me that our first point is going to be 0, 0. Right? Let's try it out. Here's our x. Right? X plus 0. Here's our y. So the first point is 0. X plus 0. 0 plus 0 is 0. Our next point is 1. 1 plus 0 is 1. If our next point is 2, then 2 plus 0 is 2. So basically, y equals x, because this goes away, right? Plus 0 means nothing. So y equals x. So whatever the x is what the y is. So that means that 0, 0 is our first point. 0, 0. 1, 1 is our second point, right? 1, 1. 2, 2 is our second point. 2, 2. So we can draw that line just like that. Let me get that straight as I can make it. There we go. We'll put our little arrows on it. And there's our other line. Easy peasy. We just need to change it around so that it comes up in this format. Once we get it in this format, then we can plug it into our table, just like this, X, and then our formula, and then Y. And then we can plot it on our graph. All right, easy peasy. You guys can do this in your sleep. Y'all are so smart. All right, that's all we have for lesson 56. I will see you in lesson 57.